Today we are going to start a new topic about the time response. Okay, in control theory. And so we have a title in here just like this one, time response. Okay, in the first place we should write the section 1 as the time response. Okay, but which response? This is the response of the dynamic systems or the system dynamic equations. Okay, in control theory we will deal with all the time with this notion, time response. For example, if our time goes to infinity, and then we will get some responses from the system, for example the position or the velocity or any other like that. But we need to analyze this response in order to emulate or in order to rechange this response in our desired path. Okay, and so this is so important, because if we want to do in anything in control theory or in mechatronic system, we will change or adjust this response in order to what? In order to select our desired parameters. Okay, and so firstly we need to write that in whole dynamic system, the time dependency determines the responses of its states or outputs. Okay, what's the state? For example, the position is a state, or velocity is a state in DC motor or any other moving objects. Okay, and so what's the output? Output is our desired output. For example, if we want to measure the velocity or the position, or if we want to control these terms, and then we will add the or change the state space matrix in order to what? In order to generate these outputs. Okay, and so in general notion we can set the proper responses of for a given system, which we call time response setting. Okay, and so if we want to adjust our response for a given input, and then we can call it the time response settings. Okay, and so if we are using the Laplace transform, and then we can take the effectors, which means that this is the input, right? This is the input, for example the force value or voltage value or the pressure value. Okay, and so we can take this effectors of the system known as, we can condition of these effectors as the poles, zeros, and system responses. Okay, so if we have any transfer function TF just like the GS, and so we can condition this system based on the poles, zeros, or it's our time response at the t goes to infinity. Okay, this is the basic notion about the time response. And so, if we have the system dynamic equation, and then we can take the Laplace transformation, or we can apply the Laplace transformation in order to what? In order to get a transfer function of these terms. Okay? After that, we can use this transfer function in order to condition our system to what? To get the proper responses of the states. Okay? And so, how can we do that? We need to analyze the output of this system. Okay? The output of the system is the watts splitting into two parts. The first one is the forced response, and the second part is the natural response. If we are talking about the output or the time response of our system, and so we will remember that we have two response, which is the first one, or the former one is called the forced, and the second one is the natural response. Okay? For example, if we have any CS or transfer function in here, just like this one, s plus 2 and s plus 5, and so we can split this transfer function into the two part, 2 divided by 5 plus s, and 2 divided by 5 s plus 5. Okay, these are the general solution for these transfer functions. Okay, and so, but how can we condition, or how can we adjust this response based on the poles, zeros, and system response? Okay, and so our basic question is that but what are they? We need to answer this question, and so we divide by 3 sections in here, just like this one, and zeros and system response. Okay. So, what is poles? Poles means that if we have the CS is equal to the s plus 2 divided by s plus 5, and so we have a poles at the denominator of this transfer function. For example, we have one pole in here as a 0, and the other pole is the minus 5. We are calling to this number as a pole, and so it's directly related to the denominator of our transfer functions. Okay, and so this determines the characteristics of time response. Okay, and so what's the zeros of the CS? Zeros means that it's directly related to the numerator. Okay, and so we have 1 zeros in here, just like this one, minus 2. Okay, and so it determines the output equals to 0 or not. It's simply meaning that we have a gain in here in order to in order to create our time response, and so we can condition our time response with the utilization of these terms. Okay, by using t0, and so we can add the zeros or the poles to set our transfer function to the new area, or the new response, or new time response, or desired response. Okay, and so what is the system response? System response means that if we have the CS in here, just like this one, 2 divided by 5 plus s, and 2 divided by 5 s plus 5. In time domain, we can solve this equation taking the inverse Laplace transformation, and then we have the 2 divided by 5 plus 3 divided by 5 exponential term minus 5t t. Okay, this is the solution of this transfer function. And so what is forced response? Forced response is equals to the what? This bias value. Okay, this is the forced response. For example, if we are going to what the t as the what the infinity, and then we can terminate or increase this value, but this term is always present in our time response, which is a bias. Okay, and so it's forced response. Whatever our response contains the t or not, and then we will have this bias value. Okay, and so how about the second term? Second term means that it's the natural response. Okay, and so it's time dependent response in this case, and then it will diminish or growing at the case of the what the exponential term, or especially for the over term. For example, if I choose this term s minus 5, and so we have a root at the 5, and so this goes to infinity value at the ct for the what the t going to infinity. But this is the natural response of our system design or system response, and then this is entirely dependent of the what the time. Okay, and so this natural, this system behaves based on this response characteristics, which is known as the natural response. Okay, so any question? There are no difference between the poles and zeros. Poles and zeros are part of the system response, okay? But we can choose the poles and zeros in here with the nomination, or with the determines to the what the output of this signal, and then we can condition this system response. Okay, this poles and zeros creates the system response, but the forced response is entirely independent of the what the poles and zeros, but the combination of the poles and zeros creates the system response. But if we have any bias term in here, just like this one, and so we have a forced, or we call it the force. And the other things, it's dependent of the time, and so this is the natural response. Do you understand that, Hosalmeddin? Do you understand that? Yes, we will deal with the time, okay? But the poles and zeros creates the transfer function, and so this transfer function yields to the system response in time domain. And so this time domain, if have a bias term in this time domain, and so we have a forced response because it's independent of the time. But the other term is a natural response because it's dependent on the time. Okay? So yes, but we don't need to do that, because I will show the proper methodology to condition the system in the transfer function domain. Okay? No, we don't need to discrete one. This entirely different topics about the discrete one. Okay? And so I will continue with the what with this domain. Okay, then so in S-plane, we can draw that. Just remember the system dynamic lesson. We have the two parts in here, which is one of them is real and this the imaginary. This calling to the the S-plane, okay? And so we have a frequency term in here, just like this one, and so the other sigma term is given in here, okay? And so how can we show our transfer function? It's in here, just like this one. Cs is equal to the what? The S plus 2 divided by S plus 5, okay? And so if we have a 0, which is given in here, we should draw the circle in here, just like this one. And so if we have a pole in here, and so we can draw the what? The x in here and minus 5x in here, okay? And so this yields to the what, or this is the representation of the what? Our transfer function in which domain? In S-plane domain, okay? And so this transfer function creates a time response. Just like this one. For example, if you have the minus 5 root in here, and so this yields just like this one, k times e minus 5t. This root is written in the what? In the over term of the exponentials, okay? And so we can conclude that if we have the poles at the left hand side, and so it always ct going to 0 when t goes to infinity, okay? We have this condition due to what? Exponential over minus 5t, because we have the negative root in here, which call it the what? It's the stability condition in our terms. And so if we want to design a controller in mechatronic system or for a given system dynamic equation, and then we will draw or we will place the roots to the what? To the left hand side of this S-plane, which is stable one, okay? And so at the origin we have a one pole. See, we have a 0, okay? And so we have the forced response. Right? Because we have this pole in here, just like this one, and so it creates to the what? Since it creates the step response, right? Because we have a bias term in here, just like this one. And so if we don't have the any pole, or if we have a pole outside of the origin or the 0, this creates to the what? The natural response, okay? In S-plane we can define these two response based on these informations, okay? And so we have a stable region where the left side of plane, or S1, 2, blah blah blah, if smaller than 0, and then we can take, or we can call it the stable region, okay? So yes, Hoselmeddin, yes, minus 5 is natural, but if we add the origin and then we don't have the natural response, this is the forced response. It's just like the step response, okay? Okay, so how can we use this information? In section 2, we will analyze the first order system, okay? So suppose that we have a system. Just like this one, we have the rs, the input value, and also we have a divided by s plus a, and we can generate what? The cs. In s-plane, we have the what? The real and imaginary parts. It's given in here. We have the one root, right? And so we can generate the cs value in here, just like this one, the rs times gs, okay, this is calling the gs. And so if we take the unit step response in here, which is represented by the 1 divided by s, and so a divided by s plus a can be given in here, and so we can generate the output based on this information. Just remember that this is the unit step in here, just like this one. We can use the ramp or the any other signal, but if we are using the unit step, and so we should transform this unit step into the what? Into the transfer function domain or the Laplace domain. We taking the unit step to the Laplace transform, and then we can generate to the what? The proper representation in here. And so this is the transfer function, and so rs times or multiplication with the what? The gs generate the what? The cs, okay? And so if we're taking inverse Laplace transform, we get to the what? The ct, right? And so in the ct we have the c forced value plus c natural value, right? And so this is equal to what? The minus 1 e a times t. This is the solution of the what? This domain, okay? And so this forced response is equal to what? The 1. And the second one, minus a, is coming from to what? To this one, s plus a, okay? And so we have also one more root in here, just like this one, but this coming from what? The input value, okay? And so this is the rs, and so this rs adds to the what? This one value in here, okay? But the transfer function cannot contain this value. But if we apply the any time dependent signal into this one, and so this cs is affected from this nature, and so this is called the forced, okay? And so we can conclude that the dynamic part is natural one, right? Because our system state is contain this information, nothing else, okay? And so we need to condition it. We cannot control the input value of this term. We can always feed the unit step, but we can condition the R system to change or rewrite the what? A value. For example, we can choose the a to 5 or 4 or minus 10 or minus 100, okay? But how can we do that? Firstly, we need to talk about the time constant, which is important parameter for the what? For the linear system, okay? Especially for a non-linear system, we have the time-dependent time constant. But just remember that we have the Cs is equal to the what? The A, S plus A, okay? And so our transfer function Gs is equal to the A, S plus A, okay? These are basic utilization. And so A determines the natural response or the transient response, right? Because the Ct is equal to what? 1 e minus at, right? This is always constant, right? But the changing part is the what? This exponential term, right? this exponential term changed in time, and so which we call it the transient response or the natural response. Okay, so how can we define that? In control theory, we can condition this a t, which is based on what the t is equal to the a, and so this value is assigned with the what, this one. Okay, and so this yields the e over minus 1, and so 0.37 or 37% is given in here, because if we have the time constant in here, which is multiplied with the what, with the t, we can assign the what, the t is equal to 1 divided by a. Okay, and so this yields the what, the exponential term over minus 1, which is equal to the 37%. Okay, but in the ct, we can have the ct is equal to 1 minus e a t, and t is equal to 1 divided by a, and so we can terminate this term in here just like this one, 30%, and so we have the 0.63 or 63% ratio of these terms. Okay, this is the standard function or standard variable. This is the inverse of the time in here, but we have a constant parameter in here which is calling to the what, the time constant. Okay, and so this value is defined with the what, defining 1 divided by a is calling to tau, which is the time constant of the response. Okay, this is the general notation or general definition for the what, for the time response. Okay, and so if we take the t is equal to 1 divided by a, this yields to the what, the 1, and exponential over minus 1 generates the 37% rate. This is the ratio of the what, the minus 1 values. Okay, this is the standard definition. Okay, this could be is the what, the 50% or the 60%, but the researcher select this value in order to what, in order to define the time response with the inverse of the time term in here, which is equal to the what, to 1. Okay, and so if we choose this 37% ratio in here, and so this ct is built with the what, with the 63% ratio. Okay, and so we can define of this term in here to decay 37% of its initial value. We can measure the response of this system based on this information. Okay, yes, standard situation, Hosarmettin. This is the standard definition. We can select what, the 50% or the 20%, but if we choose this definition, and so the computation of this system or analysis of this system can easily be done. Okay, so there's no difference because I write this graph in here just like this one. Just wait it. Hüsamettin. If we have these notations, okay, we can draw this graph in here, the ct and t. Okay, and so if we have this notation, and then we can build this graph in here just like this one. For example, if we have the 1a, and if we have 2 divided by a, and 3 divided by a, and 4 divided by a. Okay, these are the general representation. Okay, and so What about the values of these terms? Values of these terms is equal to the what? The 0.63, okay? Because we know it. And so, what about the final condition of the CT? Which is equal to the 1, because the CT is equal to 1 divided by minus AT, right? And so t is going to infinity, and then this term is suppressed from the function, and so this CT is equal to the what? Is equal to the 1, okay? And so we can write or draw this diagram based on the what? Based on this information, okay? This is our curve to what? For our time response, okay? And so this initial slope is defined with the what? With this notation. We can draw a line in here just like this one. This is the initial slope, and so this is equal to what? The 1 divided by tau a, or tau 1 divided by a. Tau is the time constant, okay? And so this value is equal to the what? The final. It's the 63% of its final value, okay? Which we calling to the what? To the steady state value. These are the definitions for this system, okay? And so this is the condition of these terms. And then if we choose the 1 divided by a is equal to the tau, or 1 divided by t is equal to the a, and then we can condition the system for the what? For the 4 tau, okay? This is calling for this system is the settling time. If we multiply our tau value by 4, and so this 4 is creates the what? The our final response, or the settling time, or the organized time for our time response, okay? And so we can condition the any other terms in here just like the one. 0.1 is equals to the what? These terms in here just like this one, and so we can generate to the what? For example, the another term in here 0.9, okay? And so this is also called the rise time, okay? This is the another parameter to define the R system, okay? And so any question? Yes, Summit. This is the basic idea, because if we generate the general response or the general term in here, just like this one, the time constant, and then we can use this notion. This the normalization value is the 1, right? This the 100% rate of the R response. It's the final response. We can scale it to the what? To the 2. But this ratio 0.63 or 63% is always kept constant at every system, and so which is called the tau, or time response, or the time constant of this system. And so the time constants generate to the what? The 63% of the final value of our system, whatever the our final response is equal to the 1 or 10, okay? It's the ratio. Okay? And so, if we generate the tau or time constant, and then we can drive the another parameters in here, just like this one, the settling time or the rise time. Okay? And so, in simple term, the tau is the natural frequency of our system or the model. Okay? We can call it just like this one. And so we can drive the any other parameters in here. For example, T rise can be defined with the what with this term. For example, if we have this information, this is equal to the 3.31 and 0.11. This coming from the what? This natural response of these terms. Okay, and so we can build the response based on the what? These terms, and then the rise time of our system can be defined with this constant. Okay, because we create the what? The time constant value in here, just like this one. Okay, these are the general basic vector for the what? For the time. Okay, we can scale it in whole time for the every system dynamic equation. And then if we take this information with the percentage values of this term, this is a normalization term of the R general response, and then we can derive this condition. And so if we choose the different time constant and then the rise time change, and basic definition of the rise time is the what? The R final response is going towards the 0.1 to 0.9 is calling the what? The rise time. Okay, this is the time between the R signal starting from the 0.1 to 0.9. Okay, see, we can define the what? The another general definition to condition the R system. Okay, and so we have also T settling time in here. Okay, and so this settling time is equal to the what? The 4 divided by A, or 4 tau in here. And so this represents to the what? The 2% of final value, or 98%, I'm sorry, initial value. This is 98% of the final value. See, and so at this time we have the what? The 0.98 value. Okay, or 98% of the what? The final value of our system. We can define it based on this condition. Okay, so any question? If you have any question, please ask me. This is the normalized plot for the what? For every response in time domain. Okay, and so this is derived from the what? The time constant. Time constant is the what? The basic vector for the time to scale the R system. For example, if I choose the 5 for the A, and so we have different response in here. Or if I choose the 10 for the A, and so we have the another response. But this ratio, this rise time formula, this settling time formula, these output values are not changed. But the scale of the what? Our system. Okay? And so do you understand what I'm saying about the time constant? Time constant are the natural frequency of our system, and so it determines to the what? To the output response or the time response of our signal, because this graph is the what? The normalized graph for the time response. Okay? for every linear system in system dynamic form. Okay? Any question? So, if you don't have any question, and then we will take a break, and after that we will start with what the 1 p.m. Okay, guys?